In this video lecture, we're going to be discussing asymptotes. So what is an asymptote? An asymptote is a line, so an imaginary line which your graph of your function would approach, as you can see in this diagram, but never touch. Right, so there are three types of asymptotes that we are going to be discussing. The first of which is a vertical asymptote, and the vertical asymptote has the form x equals to a. So this red dotted line is an example of a vertical asymptote, because observe in this picture, this function certainly approaches the red dotted line but never touches it. Similarly, we have an horizontal asymptote of the form y equals to b. So here is the red dotted line, perhaps this is y equals to positive 4. So then observe that this function certainly approaches y equals to positive 4 but never touches it. And lastly, we have an asymptote called an oblique asymptote, sometimes referred to as a non-vertical asymptote. So looking at its description, it has the form y equals to mx plus c. So observe that it does indeed contain the case of y equals to a constant. So oblique does indeed cover horizontal asymptotes but excludes vertical asymptotes, which is why we refer to it as non-vertical. Right, so an example of a non-vertical asymptote then would be, let's suppose I had some graph y equals to mx plus c, and then observe that whatever I'm about to draw certainly approaches it but never touches it. So sorry, that was my hand moving in the wrong direction, so let me just do that properly. Right, so it's approached y equals to mx plus c but has not touched it. So these are three very generic examples, just simply displaying to you vertical, horizontal and oblique. So now let's talk more specifically about vertical asymptotes. So a vertical asymptote, as we know, has the form x equals to a. So the line x equals to a is called a vertical asymptote of your graph if and only if one of the following is true. The limit as x approaches a from the left, so the limit of your function as x approaches a from the left is either equal to positive or negative infinity, or if the limit of f of x as x approaches a from the right is equal to positive or negative infinity. So this is sort of the checking criteria, but of course in order to check that this is true you would have had to guess what a should be. So luckily we have the following neat procedure to determine the vertical asymptote for rational functions. So what is a rational function? A rational function is a quotient of two polynomials. So we have a polynomial p over a polynomial q, right? And if this rational function, meaning this quotient of polynomials, is in its lowest terms, then we say the following, that the line x equals to a is a vertical asymptote if and only if the denominator, so the polynomial in the denominator evaluated at a, equals to 0, but when we evaluate the numerator polynomial, meaning p at a, then it's not equal to 0. So this is the criteria that must now be satisfied. So how do we determine this a? Of course we have our quotient of two polynomials. We first need to determine when is the denominator equal to 0. Pick out those x equals to a values and check if the numerator is not equal to 0 for those values. If that is indeed satisfied, then those values we determine from the denominator qualifies as vertical asymptotes. So let's try this example. Right, so we have our function. Let's now factorize. Right, so factorizing, because factorizing will help us determine when the denominator is equal to 0. So factorizing f of x, I observe that f of x equals to, so I'm going to pull out x at the top, and I'm left with x minus 4. In the denominator, I observe that I can rewrite this as the product of two factors, and that's going to be x minus 3 and x minus 1. Does that indeed work? Yes, it does. So now looking at this, observe that we have, so let's try x equals to positive 3, because at positive 3 we observe that the denominator is going to be 0, and we're going to try x equals to positive 1, because if I substitute in 1, then the denominator again would be 0. So we have that q, so if this is p, and if this is q, then we have that q at 3 equals to 0 and q at 1 equals to 0. So I now need to check, does p at 3 and 1 not equal to 0? Right, so what is p at 3? So plugging in 3 into the numerator, now observe that that is 3 times 3 minus 4. 3 minus 4 is minus 1, so this is certainly not 0. And what is p at 1? Plugging in 1 and 1, that's 1 times 1 minus 4, which is minus 3, and again that's certainly not 0. So therefore, by the above criteria for vertical asymptotes for rational functions, we have that f of x has vertical asymptotes, just going to use shorthand, at x equals to 3 and x equals to 1. So that is our checking criteria satisfied. Let's now move on to horizontal asymptotes. So, what is a horizontal asymptote? Right, so again, I've got a graphical representation. We know that our horizontal asymptote has form y equals to b. So it is that line which your graph approaches but never touches. Now looking at this diagram specifically, observe that, okay, this is our x-axis. As x approaches infinity, we have that the graph approaches the horizontal asymptote. And similarly here, so this is positive infinity, and on this end we've got negative infinity. As x approaches negative infinity, observe that this graph approaches the horizontal asymptote. So it's kind of pushing us towards some type of criteria. And it turns out that y equals to b will be a horizontal asymptote for your graph if and only if at least one of the following is true. Right, and what is the criteria based on what we looked at? Right, we have that the limit as x approaches positive infinity of your function f of x is equals to b, or if the limit of f of x as x approaches negative infinity is equal to b. Right, so that's the criteria, and observe that certainly these two criteria were satisfied in that graphical example. So let's find the horizontal asymptotes for this function. So all it amounts to doing is evaluating the limit as x approaches positive or negative infinity of this function. So let's check. Right. So let's do it for the limit as x approaches positive infinity of that function x squared minus 4x divided by x squared minus 4x plus 3. Remember our procedure for limits at infinity. All you have to do is find out what is the highest power in the denominator and then divide each term in this quotient by that power. Right? So doing that, divide x squared by x squared, I get 1. Divide minus 4x by x squared, I get minus 4 over x. Looking at the denominator, x squared by x squared is 1. Dividing minus 4x by x squared, it's minus 4 over x. And dividing 3 by x squared, it's positive 3 over x squared. I can now push this limit into each of the numerator and denominator and evaluate each of these terms. Recall our rule that the limit as x approaches positive or negative infinity of 1 over x to the n is equal to 0. And clearly we have, if I pull out the constant, I've got 1 over x to the power 1, similarly there. And if I pull out the constant, I've got 1 over x to the power 2. So I know that the limit of these two terms are 0, and similarly of that term is 0. So that means that I have the following: the limit as x approaches infinity of a constant divided by the limit as x approaches infinity of a constant, since I know these three terms all go towards 0 by this rule which we had learned previously. And the limit of a constant is the constant, so therefore I've got 1 divided by 1, which is 1. So what this now means, based on that checking criteria, is that therefore y equals to 1 is a horizontal asymptote for that function. Now observe that similarly, if I had to replace this by negatives in the limit, so if this was the limit as x approached negative infinity, I will still arrive at the same answer. So once again, y equals to 1 is indeed a horizontal asymptote. Now finally, let's move on to oblique asymptotes. Alright, so moving on to oblique asymptotes. What is an oblique asymptote? Remember, we had seen that its form is y equals to mx plus c, and I explained why we refer to it as a non-vertical asymptote. So y equals to mx plus c is a non-vertical asymptote for your graph if and only if at least one of the following is true: the limit as x approaches infinity of your function f of x minus y equals to mx plus c, so meaning minus mx plus c equals to 0, or similarly, if the limit as x approaches negative infinity, evaluating the same function, equals to 0. So let's consider the following. What does this now mean? So suppose that I had given you a rational function. Meaning a polynomial divided by a polynomial, which is of the form p of x divided by q of x. And suppose that the degree of the polynomial in the numerator, meaning p, so degree of p is 1 more than the degree of q. So for example, maybe the degree of the polynomial p was 3 and the degree of the polynomial q was 2. So there was an x cubed in there, and at the bottom there was an x squared. Right. Then because there is a higher degree in the numerator than the denominator, I can now divide these two polynomials. So upon long division, so after long division, so you need to ensure that you remember how to do your long division. Right, so after long division, suppose that we had that f of x now equals to, so we would get out mx plus c plus your remainder. So I'll call that remainder r of x divided by q of x, which is our divisor. Right, and of course where m is not 0. Then we kind of now have a method to determine what the non-vertical asymptote would be, because we would now expect that the mx plus c, which we obtain from long division, would be that non-vertical asymptote. And observe that if I needed to compute the limit as x approaches positive or negative infinity, then it amounts to simply saying that I'm taking f of x minus, so f of x minus mx plus c will then give me back the remainder divided by the divisor. So the limit of this now becomes the limit of r of x divided by q of x. And if this equals to 0, then that means we have a checking criteria to determine the non-vertical asymptote for a function which is a rational function. So keeping this in mind, let's approach the next example. Right, so we've got a function 10x squared plus 9x plus 5 divided by 5x plus 2. So we have our criteria. What we would like to do is, since this is a higher degree than the denominator, we're going to take that polynomial and divide it by that. So let's do the long division. Right, so 10x squared, I'm just copying what I can see, divided by 5x plus 2. I want to determine what is the remainder. Right? So what is 10x squared divided by 5x plus 2? It is 2x. Right, so I've divided first. Remember, your method is divide, multiply, subtract, and bring down if necessary. Right, so I've divided. I now need to multiply. So what is 2x multiplied to 5x plus 2? It is 10x squared plus 4x. I now need to subtract. So take those two terms there and subtract from it what I've put into the brackets. So that gives me 0. And then I've got 9x minus 4x, which gives me a value of 5x. Right, and then repeat the procedure. There was nothing to bring down, so I'm going back to divide. What is 5x divided by 5x plus 2? So then that gives me a value of 1, because 5x can be divided by 5x once. And now I need to multiply. So now when I'm going to be multiplying, it's 1 times 5x plus 2. So that gives me 5x plus 2. And after I've multiplied, I need to subtract. So let me bring that down. Right, and now upon subtraction, observe 5x minus 5x is 0, and 5 minus 2 is positive 3. And this is where I now end, because I've received a constant. So this is the remainder, r of x. So that means that this equals to mx plus c, which is 2x plus 1, being added to rx divided by q of x, as we had seen in the previous slide. So what is mx plus c? I've said it's 2x plus 1. And what is our remainder? It is 3 divided by 5x plus 2 from the denominator. So there we have it there. So now the question is y equals to 2x plus 1 an oblique asymptote, or a non-vertical asymptote for this function f of x? We now need to check by evaluating the limit. So I need to take the limit as x approaches, well, we can do x approaches positive and negative infinity of, we're now going to be evaluating f of x minus 2x plus 1. Because we are guessing that this here is our non-vertical asymptote. But what is f of x minus 2x plus 1? It is precisely that, based on our long division calculations. So it's 3 divided by 5x plus 2. But then once again, this is limits at infinity of this rational function. So we divide both the numerator and the denominator by the highest power of x. Right? And when you're doing that, so that's 3 over x. This is 5 plus 2 over x. I've divided 3 by x, I've divided by 5x by x, and 2 by x. And then you can now push this limit into both the numerator and the denominator and in the individual terms. Once again, because we know that the limit at positive and negative infinity of 1 over x to the n is 0, I know that this will be evaluated and give me 0, and that will be evaluated and give me 0. So I observe that my final answer is indeed 0. And that is the criteria that needed to be satisfied. Let me bring back the previous slide. So if we evaluate the limit and get out an answer of 0, then y equals to mx plus c is indeed an oblique asymptote. So this is an oblique asymptote. asymptote, and that is your check-in criteria. So ensure that you remember the definitions and the criteria to determine each of a vertical, horizontal, and oblique asymptote.